Every second, your phone sends messages, videos, payments, maps, and searches across the planet. It feels wireless. It feels like everything is moving through the air. But the real internet is not floating above us. It is lying in the dark, cold, silent floor of the ocean. That is the strange truth. The most modern communication system in human history still depends on physical cables thinner than most people imagine, stretched across thousands of kilometers of seabed. Without them, the global internet would not disappear completely, but it would become slower, weaker, more expensive, and far more fragile. And here is the question that makes this story so interesting. If we have satellites, rockets, Starlink, 5G, and wireless everything, why does most international internet traffic still travel through the ocean, not through space? The answer begins with a simple misunderstanding. Wi-Fi is wireless inside your home. 5G is wireless between your phone and a nearby tower. But once your data leaves that local network, it usually enters fiber optic cables. And when it needs to cross an ocean, fiber does something satellites struggle to match. It moves huge amounts of data with very low delay. Think about a video call between New York and London. The sound and image do not simply jump through the sky. In most cases, the data travels through terrestrial fiber, reaches a landing station near the coast, enters a submarine cable, crosses the Atlantic, and comes out at another landing station on the other side. This happens because fiber has enormous capacity. A single modern submarine cable can carry staggering amounts of information through multiple fiber pairs and wavelengths of light. Satellites are useful, especially for remote places, ships, aircraft, and emergency connections. But for the heavy daily load of the global internet, cables are the main highway. Very few people see this infrastructure because it is designed to be invisible. The cable comes ashore at a landing station. From there, it connects to national networks, cloud regions, internet exchanges, and data centers. To you, it is just a loading bar. To the network, it is a chain of physical places. According to TeleGeography's 2006 submarine cable map, the world has hundreds of cable systems and thousands of landing stations. Their fact says there are more than 15 million kilometers of submarine cables in service around the world. That is enough cable to wrap around Earth many times. But the real surprise is not just how many cables exist, it is how much we depend on them. The International Telecommunication Union describes submarine cables as the backbone of global communications, carrying roughly 99% of international data traffic. In other words, the internet may feel like a cloud, but the cloud has roots under the sea. So why not replace it all with satellites? The first reason is latency. Satellites have to send signals up and down through space. Even at the speed of light, distance matters. Low Earth orbit satellites reduce this delay, but they still face limits, handoffs, spectrum constraints, weather, ground stations, and orbital complexity. Fiber is not magic either. Light travels slightly slower inside glass than in a vacuum. But submarine cables often take direct, high-capacity routes between major economic centers. For banks, cloud platforms, video calls, online games, and trading systems, a few milliseconds can matter. The shortest practical path is worth real money. The second reason is capacity. A satellite has limited bandwidth shared across many users and regions. A cable can keep adding capacity through advanced optical technology, better terminal equipment, and multiple fiber pairs. That is why big tech companies invest in cables. They need to move oceans of data between continents. And this is where the story becomes less like a tech gadget and more like global infrastructure. A new submarine cable is not just a wire. It is a multi-year project involving route surveys, permits, landing rights, cable factories, specialized ships, repeaters, financing, and international politics. Before a cable is laid, teams study the ocean floor. They avoid deep trenches, volcanic zones, fishing areas, anchor zones, and steep underwater slopes when possible. The goal is simple: find a route that is fast, safe, repairable, and politically possible. Then the cable ship arrives. These vessels carry thousands of kilometers of cable in giant tanks. Slowly, carefully, the cable is fed into the ocean. Near shore, where human activity is highest, it may be buried under the seabed for protection. In deeper water, it can simply rest on the ocean floor. This is not a fast job. A ship may move slowly for weeks, following a route planned long before the first meter of cable touches water. The crew has to watch weather, currents, seabed conditions, shipping routes, and the tension on the cable itself. Too much tension can damage it. Too little control can place it in the wrong location. The cable itself is a small miracle of engineering. At the center are glass fibers. Around them are layers of protection, steel wires, copper, insulation, and waterproofing. In shallow areas, the cable is thick and armored. In the deep ocean, it can be surprisingly slim. But light weakens over distance. So every few dozen kilometers, repeaters or optical amplifiers boost the signal. These devices must work for years in places humans cannot easily reach. If one fails, fixing it is not like unplugging a router. It can require a ship, a grapnel, calm weather, and time. The repair process feels almost impossible when you first hear it. A ship travels to the suspected fault area, lowers equipment into the sea, finds the cable, brings it back to the surface, cuts out the damaged section, splices in a new piece, tests the signal, and lowers it back down. All of this can happen in rough water, far from land, on a cable most people never knew existed. And cables do break. Not every day for every cable, but often enough that an entire repair industry exists. The most common causes are not dramatic spy stories. They are anchors, fishing gear, earthquakes, underwater landslides, abrasion, and accidents. The internet is advanced, but it still has to survive the physical world. This is why cable routes matter geopolitically. If several cables pass through the same narrow sea, choke point, or politically tense region, the world pays attention. Recent concerns in places like the Red Sea and Baltic Sea have reminded governments that the Internet's hidden infrastructure is also a strategic target. But the system is not as fragile as one cable. The Internet was built to route around damage. If one path fails, traffic can often move through another. The problem is congestion. If too many cables fail in the same region, data does not vanish, but it may slow down, reroute, become expensive, or lose redundancy. That redundancy is why the map matters. A country with many landing stations and several independent routes has more options. An island or smaller economy with only a few links has less room for error. For some places, one cable is not just a cable. It is a lifeline to banking, cloud services, hospitals, education, tourism, government systems, and the outside world. This is the real lesson. The Internet is not one thing. It is a mesh of cables, routers, data centers, satellites, towers, power grids, and agreements. The reason it usually works is not because it is weightless. It works because an enormous physical machine is constantly maintained by people most users will never see. Satellites are still important. They connect isolated communities, aircraft, ships, disaster zones, and places where cables are impossible or too expensive. They can also provide backup, but they are not the main pipe for the global internet. They are more like an essential bridge where the highway cannot reach. And that is why the satellite story is not wrong. It is just incomplete. Space-based internet solves a different problem. It brings connectivity to places that cables cannot easily reach. But when billions of people stream video, move cloud data, make payments, and talk across continents, the heavy traffic still needs the quiet power of fiber. So the next time your phone instantly loads a video from another continent, remember what probably happened. Your data did not simply fly through space. It became light, entered glass, crossed a continent, dropped into the ocean, raced through a cable in the dark, came back to land, and reached a server or device on the other side of the world. The internet feels invisible because the best infrastructure disappears from daily life. But the truth is more fascinating than the myth. The modern world is not held together by clouds. It is held together by glass strands, buried under salt water, protected by ships, engineers, and maps that most people never see. And that is why the internet is under the ocean, not in space. Because sometimes the fastest way to connect the future is still a cable lying quietly at the bottom of the sea.